Let's go ahead and cover some topics with just one mean. In this question, Congress is trying to regulate the fuel economy for gas mileage on cars. Now, the important thing we need to be able to do is identify every single bit of notation in this problem. You'll notice we have 36.6, we have 29, 39.6, and 4.76. With this in mind, each of these have a different notation. So pause the video here and see if you can identify what these are. If you could write down what 36.6 is in notation. Is it mu? Is it mu naught? Is it x bar? Okay, let's see if you got everything right. So 36.6 is what we are going to test. It's what we're going to hypothesize to be true according to the null. So I've got my cheat sheet over here. And mu naught is 36.6 because this is the tested mean or the hypothesized null mean. Next, we have 29. 29 is how many cars we chose at random. So 29 is going to be, or the trips or the cars, that is the sample size. So with this in mind right here, we have 29 company trips chosen at random, so that is the sample size. Next, we have the mean from these 29 trips, and that's important. We have to realize this is the mean from the 29 trips, so that is the sample mean. Now, when we do the sample mean, it's important to know we can call it x or y bar. It just means mean of that variable. So this is the sample mean, 39.6. It relates to the sample size. Next, we have 4.76, very important because this is also a sample standard deviation. Sample standard deviation is S, where the population standard deviation would be sigma. We are not interested in sigma though. We are interested in S. We do not know the true standard deviation of this problem, which leads us to a T-statistic. Now the T-statistic is something that we need to review and make sure we understand what it is. It is just going to tell us how many standard errors of the mean our observation falls away from our hypothesized mean. With this in mind, this T has n-1 degrees of freedom. Not too hard to solve here, because n is 29, so what this means is we are dealing with a T with 28 degrees of freedom. This is a specific T distribution now. Just so you can see, what we're looking at here is a certain T distribution with 28 degrees of freedom. So it'll look like that. Kind of looks like the Z, but it is a T with 28 degrees of freedom, and that is what the degrees of freedom tells you. It tells you which T you are using. Next, let's go ahead and write the null and alternative for this problem. The null and alternative are going to be similar in most respects because the null will always have the equal sign. So you can cancel out this one right there. That is incorrect because it has a does not equals in the null. So reading this, we would say the null states that the true mean mile per gallon fuel economy that the car is getting. A lot to say there. That's what the mu means right there. The true mean miles per gallon that we are getting is equal to 36.6. Now, if you remember, that is our hypothesize. This is mu naught. So this actually says mu equals mu naught. Very important that we realize mu naught is always going to be on the other side, whatever we hypothesize to be true according to the null. Now we need to look at the alternative to figure out what we want to show evidence of. And a good question, or one that's easy to find the answer for, is something that says, is there strong evidence that we have obtained this fuel economy? So is there strong evidence we've obtained our fuel economy goal? To meet our goal, we need to have at least 36.6. That's what we're aiming to get. So to meet the goal, we would hope to have evidence for the alternative. Here's our alternative. We hope there's evidence for the alternative that the true mean miles per gallon is greater than 36.6. And this is definitely our null and definitely our alternative. Next, when checking conditions, remember, we have three conditions here. Condition 1 is going to be random. And we know it's random because car trips were chosen randomly. Next, we have 10%. I think it says this is a large company. Yeah, a company with a large fleet of cars. So if they have a large fleet of cars, well, also they're checking certain trips. So maybe these cars would even be capable of more trips. It's 10% of all trips our cars would take. And hopefully we randomly select the cars, like we said earlier. And then 10% of all trips, well, I suppose we have more than 290 trips. Why 290 trips? Well, because our sample size is 29. So we have to sample less than 10% of the whole population of trips, that is. Now, finally, we need to check a specific condition related to what kind of data this is. Our third condition will be related to if it is quantitative or categorical. And that doesn't mean the third condition is quantitative or categorical. It means if it is categorical, what the data we are collecting, if the data we are collecting is categorical, the third condition will be success-failure, where we need 10 successes and 10 failures according to the null. If the data is quantitative, then the third condition will be that our distribution is nearly normal. And there's lots of ways to check that. So let's see what kind of data we're collecting. We are collecting miles per gallon, which is a quantitative amount. So with this in mind right here, we are checking the nearly normal condition. With this in mind, let's take a look. All of these have that the sample is random, so that's good. And if the sample is random, then we can assume they're independent, so this B and C are wrong. Next, we would say if there are no outliers and the data is unimodal and symmetric, and only mildly is skewed, one can assume it comes from a normal population. That is right there, the important part. This is checking the nearly normal condition for us, where this one down here, we could use it if the data was categorical, but we were not collecting categorical data up here. Categorical data would be like male, female, yes, no. So the correct answer is this one. We have random, 10%, nearly normal, and hopefully we pass all those. Unfortunately, it did not show us the original shape of the distribution. We just have to hope that it was kind of unimodal, not a strong skew. Describe the sampling distribution model of mean fuel economy for samples like this. So now we want to see how far our observation is from the expected. So anytime we do this test right here, this one sample t-test, we will always use the same equation. It's right here. T equals observed, which is our sample mean, minus mu naught, which is our hypothesized mean, over standard deviation over the square root of n. And when we take a look at our answers, we have our sample mean. It needs to be right here, sample mean. So this is only where the sample mean is at, right there, y bar. And then we have our hypothesized mean right here, which this is the only one that has the right order. So if you notice this, it does follow y bar minus mu naught over s over square root of n. And we said it would be a t with 28 degrees of freedom. That is how many standard errors of the mean we are away. This bottom portion of the formula, this 4.76 over square root of 29, is the standard error of the mean. And once again, every test statistic is just a difference. All we're seeing is how far our sample mean is away from our hypothesized mean, and then we're standardizing that difference. Very important. Now the p-value takes one more step. We still haven't found it, and we need to solve for this. So let's go ahead and solve it right here. I'm going to bring the calculator to the right a little bit. And our sample mean, let's turn our calculator on, 39.6 minus 36.6. That's just our difference right there. And that was easy enough. It was just 3. Now we have to take the standard error of the mean. So let's go ahead and take 4.76 and divide by square root of 29. This is the standard error of the mean, and that should turn out right. And then let's take 3, divide by second answer. Now, I've seen people stop here, and you can tell that this is the t-statistic. This is not your p-value. This is our t with 28 degrees of freedom, 3.394. What you have to do with your t is it tells you how many standard errors of the mean you fell away. So we have to go back to the t-distribution. This is statdistributions.com/t, and you have to put in your t-value right here. That is required, and we need to do a right-tailed test. 0.001, that is our p-value. When you look at it, here's where our results landed. The p-value shows the probability of our results or results more extreme happening if the null is true, or given the null is true. With this in mind, 0 is at the center right here. If we had landed at 0, it means we would have landed at the null value of 36.6. We would have landed right on top of what we expected according to the null. And values such as the null or higher than the null would occur 50% of the time. And why am I doing higher? We are doing a right-tailed test. If you look at the way the alternative points, you can get an indication of which way to shade. The greater than shades to the right, the less than shades to the left, and the does not equals points both ways, so it shades both ways. And we can view this right here if we click left tail, so that would be the left tail test, the less than, right-tailed test, so greater than, and the two-tailed test, which I misclicked, and there it is. This is the two-tailed test, and it's really hard to see, but it doubled my p-value, and we're also shading down here. So if I go to the right tail, it's half, and it's very hard to see because my p-value is very small, and the test statistic is very far away. The test statistic is the standardized result. Remember, this is just how far away we fell, standardized. So this means how many standard errors of the mean I am away. So I am 3.394 standard errors of the mean. The probability of this happening or events more extreme, according to the null, is very small. And yes, we have a small p-value, 3 decimal places, 0.001. Not likely to occur. Given that it's not likely to occur, so right here I think we have a good answer. Let's read it. If the average fuel economy is 36.6, the chance of obtaining a sample mean of 39.6 or more by natural sample variation is 0.1%. That is perfect almost. I mean, different statistician might say a different thing, but that's really good. It's saying if the truth is 36.6, the results we saw are very unlikely to occur. If the truth is 36.6, what we saw, just take a look again at this. If the truth is right here, because this is where 36.6 is at, because there's no difference from that if we landed there with the sample mean. If the truth is 36.6, getting far over here is not likely to occur. It's like a dartboard, and we say we hit this big dartboard. Well, it's not likely that we would land all the way over here just by chance. This is an odd result. So let's go back here. Since this is odd according to the null, like this would not be likely to happen according to the null. Results like this are more extreme. It only happen 0.1% of the time, basically 1 in 1,000. This means what? It means let's reject the null. Using a 0.05 as the p-value cutoff, there is strong evidence that the company is meeting their goal. And just think about that for a moment. They take a bunch of cars out on trips. Let's go back to it. They take a bunch of their cars out on trips, and the cars get almost 40 miles per gallon. And so do you think they're meeting the standard? Well, we should use statistics to make, more inference than just, well, that sounds good. But it sounds credible. Just when you think about it, we get 40 miles per gallon. Are we meeting the standard of 36.6? It seems like we have good evidence. And that's what statistics is all about, is putting that difference of 3, which we have 36.6 to 39.6, taking that difference, putting it in context and saying, would this be likely to happen if we aren't meeting it? And if we aren't meeting it, this would not be likely to happen. So this shows evidence we are meeting it. Okay. It looks like time for some confidence intervals. And one thing I'm going to show here on this as it reloads, let's show it with the calculator test right here. Once again, always good to know how to do it 2 ways. I'm going to try to do every problem on here 2 ways. If I go to stat test, I need to do a t-test because this is a 1 sample test of means. And I'm going to input the statistics and go here to mu naught. Once again, labeling stuff is very important. X bar is our sample mean. And let's hit enter. And then our sample standard deviation was 4.67. 4.76, excuse me. Sample size is 29, and we are going to have to shade to the right. So once again, read this. This says mu greater than mu naught, and that is our alternative, just so you can see here on the screen. Once again, mu naught is the value of 36.6, so mu greater than 36.6 is the alternative written right here. And so you even have the alternatives on your screen down here. This is literally mu greater than mu naught, so whatever you put in the value of mu naught is the value that goes right here. So let's go ahead and hit draw on this. Let's go down and draw and see our pretty curve, which we're barely going to be able to see the results. If you have a TI calculator, it is possible to do a lot of these questions, but sometimes we ask a question in such a way that you might not be able to input everything. So it's good to know both ways on how to doing it. Understand how to do it by hand and understand the calculator way. And the exact same results is what we get that we were able to do pretty easily by hand. Okay. How far do the golfers at a country club drive the ball? So when you drive the ball, that is a quantitative amount. And well, look at that. We got a little histogram over here. Histogram looks to be kind of unimodal, a little bit symmetric, and also not really any outliers. That's not too crazy. I mean, it's a mildish outlier. I don't know. So with this in mind right here, we have the sample mean and the sample standard deviation. And you have to watch because we see count right here, and that may confuse people. I don't like that it says count. I would prefer it said sample size. That is the sample size. And once again, we need to go to our notation and see what we have. So for n for this problem, let's delete out what we have first. Let's make a new problem right here. In our new problem, we are not doing a test, so I'm just going to put x next to this because it does not exist. Or let's write some math notation, does not exist. We're not using that. So we do not have a hypothesis. We're not saying, do they drive it this far or further? We're not doing a test. We do have a sample size, though. And we do have a sample mean, which I did not remember there. Once again, first thing you want to do is record all of your notation whenever you get to a problem. 287.4. And we do have a sample standard deviation, 8.14. Let's go back to that. 8.1. 8.1. So now I think we have everything, but our t is slightly different because our sample size is 202. Our degrees of freedom, because this is a one sample t. Remember, degrees of freedom are based on what type of test or interval you're making. This is one sample, so degrees of freedom are n minus 1, n is 202. T is 201. That is what we must do here. Write down all the notation for all the numbers. Make sure you have all of these memorized and know what they mean and know how to identify them in problems. So we do not have all this yet. Let's find one last thing here. It wants us to build a 95% confidence interval. So you must use a t-applet for this. This means 5% will be shaded on a t with 202 or 201 degrees of freedom. And if you're anything like me, it's going to be close to 1.97. Or 1.96, and let's do it properly. Let's do two tails, and there it is. 1.97, 1.96, and why do we know this? Because the t is like the z. As the t gets more degrees of freedom, it rises up into the z, and you can see that here as I show it rise up. So if you notice there, it's rising up, and it turns into the z, basically. It needs infinite degrees of freedom to be the z, and you see what we know for our z of 95% confidence interval. But this is kind of close enough, and I had 201 degrees of freedom, and that's so close, 1.972, basically what we would see with the z. So let's go here, 1.972. That is what we're going to have to use to build our 95% confidence interval, and we need to go to the formula now, one of our classic formulas for a t-interval, right here. We need to take the sample mean plus or minus, and this is our confidence level, and then times it by the standard error of the mean, which is s over square root of n. And we just used this s over the square root of n in the previous formula. It was the standard error of the mean again. It standardizes things. We always need a center for our interval, a confidence level for our interval, and a standardizing factor for our interval. Once again, this is an interval to estimate the true mean, so our best guess of the true mean is the sample mean. Whatever you see in this first position is going to be what you're making an interval for. Not that we're making an interval for the sample mean. It is an interval made from the sample mean to estimate the true mean. That's very important. Whatever you see here, you want to estimate the truth for this. So let's go ahead and start calculating. So bring up our calculator, put it towards the middle of the screen this time. And we need to calculate first the margin of error, which was s over square root of n times t. So s over square root of n, 8. I have to turn the calculator back on. 8.1 divided by square root of n. So this is s over square root of n, and then you take this and times it by your t-statistic. There we go. So that is the margin of error. To be very clear, I'll show you here on the formulas, I just did all of this math right here. I put in s, divided by the square root of n, and I times it by the t-statistic that I found. The t-statistic is specifically what creates a 95% confidence interval with the right amount of degrees of freedom. If you notice, there's 95% shaded here in the middle. To make it a little more clear, we can also view it by clicking on this one, 95% in the middle, which is 5% on the outside, which was what I was previously showing. So with this in mind, we have solved for the margin of error. The margin of error is the plus or minus. This is the plus or minus. So all we're doing is going up or down this amount from the mean, because now all we have to do is take the sample mean. This is 1.12, which is the margin of error. And then we can add and subtract that from 287.4. And let's just get the positive of this. You would add 287.4, and that's the positive 287.4, and minus to get, and our margin of error was 1.123. And this is our interval, 286.2 or 286.3 rounded to one decimal to 288.5. And we can do this very quickly with the stat tests, and we want to go to T interval right here, T interval, introduce the statistics. Our sample mean is 287.4. Our sample standard deviation is 8.1. Our sample size is 202, and our confidence level is 95, and calculate. And we should have exactly what we had before. See here in a second. 286.3, as I said, and 288.5. So let's see here, 286.3, and I think 288.5, as long as sometimes the hardest thing is remembering the numbers. There we are. That is our confidence interval. I am 95% confident that the true average distance that people are driving the ball is contained in the interval 286.3 to 288.5. Very important we say I am, and say your confidence level. Probably a good idea to say it out loud if you're practicing right now. I am 95% confident. This is the hard part. That and you have to read what is right here, that the true average distance people are driving the ball is contained in the interval. And you see it shows that right here. It's contained in the interval. I am 95% confident the true average distance people are driving the ball is contained in the interval 286.3 to 288.5. Very, very important. Rewind and listen to it again. Make sure you can interpret any interval like that. Very important. Okay, to the harder questions down. Oh, there's more to this. What is the problem with this experiment? Did they not randomly take it? Let's look. So this 10% condition is not the problem. And the histogram shows that the data is skewed. No, it's not skewed. It's got to be the first one. Oh no, look at this. The leading golfers. Oh no. If it wants me to compute an interval, I'll compute intervals all day long, but that was not random. So that's the problem. Continue on here. The data are the mean driving distance for each golfer. Is that a concern in interpreting the interval? And when you think about this, so with the means right here, this is going to show us what we would expect on average from each golfer. So there's going to be less variability in this, because what we're trying to do right here, if we're trying to figure out the average driving distance, then we really want to see that variability. And this is not the original distribution, because we're kind of taking the mean of the means. And so this isn't an accurate depiction to figure out, the average driving distance of our golfers, because we're just taking, this is not the way when you think about how we do our statistics. We didn't take a car and find the mean for it and then take other cars and look at their means. It's a different idea in this problem. So there is problems with this. We would want to go to individual golfers and, randomly take samples from our golfers. And then we could figure out the average driving distance of our golfers. And so this is a problem. The best way to do this experiment, if you had 1,000 golfers at your country club, go out and just collect samples from people, maybe mark certain balls. That's probably the best way. Put a little chip inside of them. And then, that's a great idea. Put a chip inside of, like 20 of the balls that somehow doesn't affect it by some sort of special balls that will go the same distance if they're hit the same way. And then you could talk about the average driving distance at your country club if people are randomly getting those balls. If for some reason the 5 balls are all together and people keep getting them and one golfer keeps getting them, it could cause problems. But you would want to kind of have random selections of what people are doing, not the means. That is a problem. Very difficult kind of in-depth question or concept there. A student on the track team wants to test whether her times to run a mile are different after a new training regimen. Previously, her average time running a mile was 8 minutes, which is an appropriate alternative hypothesis. Now here's the thing. She wants to test if they are different. This is key. And we have to remember when we do the alternative, we need to be able to read it. So we need a two-tailed to see if it's different. So she wants to see if there is evidence that the true mean run time for her miles is different than 8. So next, suppose we construct a 90% confidence interval for a mean. This is equivalent to a two-tailed test with which level of significance. Some great stuff to look at here. We can go back and think about it for a moment. Let's say we construct a 90% confidence interval. If we were to run a test, generally we think about the test being two-tailed with alpha levels on the outside. And if you take a look, 90% on the inside is 10% on the outside. So nice and easy there. They correspond and would be kind of doing the same exact thing. So you'll get the same results. This is to say, if you do a test with 10% alpha, and let's say you test a value, like the previous girl tests 8 minutes, and she rejects the null, that means if she makes a 90% confidence interval, that 8 would not be in there. Kind of a good kind of conceptual question. Which of the following is not a condition to check to estimate the mean of a population? Very, very easy, because we would not check the success failure condition. That is a categorical condition. So do not check this with quantitative data. A medical researcher measured the pulse rates, beats per minute, of a sample of randomly selected adults and found they followed a student T based confidence interval. Found the following student P T based confidence interval with 95% confidence. We have that the true mean is contained, true mean of pulse rates contained in the interval 63.13 to 67.09. Explain carefully what the software output means. There we go. We are 95% confident the interval 63.1 to 67.1. 63.1 to 67.1 beats per minute contains the true mean heart rate. That is excellent. And I interpreted, I am 95% confident the true mean pulse rate is contained in the interval 63.13 to 67.09. Make sure you know how to interpret an interval. What is the margin of error? So the margin of error is half the length of the interval. If you think about an interval, all you need to do is cut that interval in half to find the plus or minus. Remember, start here in the center. The margin of error would go up the same amount and down the same amount. So let's cut the interval in half by finding out how long it is first. 67.09, one decimal place, so we're all right by doing this, to 63 point, and you might ask why I'm doing it this way. If you take the big number minus the small number, you get a positive difference. Divide by 2, half the length of the interval is 2. You can almost just eyeball that one and say, oh, just look at it and say, that's about 2 away. If you think here that if you add 2, this goes to 65.1, and if you add 2 again, this goes to 67.1. Just think about that. 65.1, if you round this to 63.1 and 67.1, 65.1 would be in the middle. Or just do this, round this to 63, and then if you add 2, you get 65, and round this to 67. That's just the margin of error is how much you have to add to get to the middle and then to the top part. That is your margin of error. So they made a 95% confidence interval. What would have happened if they made a 90? If they made a 90, then their interval is going to be smaller. Because think about this. If I tell you I am 99% confident that something is in the interval, I'd have to make my interval wider because then it might contain it. But if I tell you I'm 1% confident that it's in that interval, it doesn't sound like that's a big interval. So the more confident you are, the wider your interval needs to be to possibly contain it. That's some good questions there. So let's go ahead and take a look at this data. Whoa, that data is skewed. It's got an outlier like crazy. This is 20 CEOs with a range of 0.1 to 61.44 million. And I would take that 0.1 million. That's 100,000 per year. That sounds good to me. The average is 17.725, and that is a skew. So the histogram box plot is shown based on the data. A computer program found that a 95% confidence interval for the mean annual compensation of all CEOs is negative 6.63 to 42.08 million. Why should you be hesitant to trust this confidence interval? The assumptions are not met. This has a very large outlier. That is our problem right here. I think some other versions of this problem might show you some bimodal data. See here, hit similar question. Ooh, look at that skew. That is skewed. And it's only 20 CEOs. So this is a very skewed, and this is too small of a sample size for only 20. The distribution is too skewed for a sample size of only 20. We would only want a little bit of skew. So kind of some good concepts there. You need, if it's really skewed like that, you might need a sample size of like 50 or 75. A medical researcher tested a new treatment for poison ivy against the traditional ointment. He concluded that the new treatment is more effective. Explain what the p-value of 0.025 means in context. So the p-value is the probability of our results or results more extreme happening due to random chance variation given that the null is true. So if there is no difference in effectiveness, if the null is true, because that's the null, is that there's really no difference, the chance of seeing an observed difference that is large or larger is 2.5 by natural sampling variation. Once again, the probability of our results or results more extreme happening due to random chance variation given that the null is true. And that is in line with what I always say right there. Aha. 2 more questions. A statistics professor has observed that for several years, students scored a 110 out of 150 on the semester exam. A salesman suggests that he try a statistics software package that gets students more involved with computers, predicting that it will increase students' scores. The software is expensive, and the salesman offers to let the professor use it for a semester to see if the final exam increases significantly. The professor will have to pay for the software only if he chooses to continue using it. That's a good deal. I'm trying to get him hooked, though. Is this a one-tailed or a two-tailed test? Now think about this. If it's a two-tailed test, going back to our first question, that means it does not equals. So he's trying to find evidence if there's a change. But change could mean grades got worse. So this is one-tailed test because we want to see if it's evidence that the scores are increasing. So this is a one-tailed test because we're only interested in the one direction. You can think of tails as in directions. So if you're saying it's increasing, that's one-tailed, decreasing, it's one-tailed, or change is two-tails because it could go up or down. You can find evidence of that. Yes. My enter button is not working. There we go. Now it works. Write the null and alternative. And I love this one right here because this is good practice. Null has the equal sign. We want to find evidence of greater than. That is where people have a tough time because they can't decide to put p or mu in here. Now, this chapter is always the same, but remember, he's looking at their final score. So this is the true mean. And I wish they had more things in here. I wish this was flooded with options. And what he wants to test against is he's saying if there's no change, like if this software doesn't help, they will still get a 110. But if this software does help, and I chose the wrong sign, if the software does help, then there'll be evidence that the true mean is greater than 110. If it really is helping, we would think we'd find evidence. So this is an excellent question right here. Good practice. And if you can get this question right, you probably understand how to write nulls and alternatives. That's a very good, and you should understand why to put the mu in there because we're testing the true mean, where p would be testing the true proportion. In context, explain what would happen if they make a type 1 error. In a type 1 error, it's a false positive, I say, where we reject the null. You have to understand specifically what a false positive is, though. When I say positive, I mean evidence, positive evidence. So when you hear me say false positive, think false evidence, because it's like, it means like, aha, I found results. So it's false evidence. What does it mean to have false evidence? Evidence is the alternative. So you have false evidence for the alternative. So a false positive is when you have evidence for the alternative. Very important once you always understand what in context it would be. So our alternative here is we have evidence for that the true mean is greater than 110, but that's wrong. Every time I say false evidence, it means we have evidence for the alternative, but we shouldn't. So the professor is going to buy the software, which doesn't help the students. There we go. He's going to buy it because he says, oh, I've got evidence that their grades increased, but that's not true. He should have maintained the null. So in a type 1 error, the null is true, and we reject it. So a type 2 error, let's look here. It's simply the reverse. I would call it a false negative. Very important what we know what that means. That means false no evidence. So if we have false no evidence, we continue to believe the null. And if that's false, we should have rejected the null. So with this in mind right here, he doesn't buy the software because he's gonna have no evidence, but that's wrong. Very important. What is meant by the power of this test? Power is a very in-depth concept that I ask you should review if you have no idea what power is. There are 3 things that affect power: sample size, effect size, and alpha level. So power is the ability to reject the false null. So if the null is false, we should be able to reject it with a powerful test. So if this test is powerful, think about it. We should be able to reject this when it is false. In other words, we can find that the software is helping. That's all it means. Power is the ability to reject a false null, so we'll be able to see that the software is helping. The power of the test is the probability of correctly deciding the software is helpful. Okay, more nulls and alternatives. Yes, love it. So a statistics professor has observed that for several years, students score on average a 106. The salesman suggests that he try statistical software package that gets more students involved with computers, predicting that the students' scores will increase. The software is expensive, yada, 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 basically the same type of question. The professor will pay, in the trial course that uses 217 students scored 109 points on the final with a standard deviation of 8.8. So same type of question here. And we just have to remember how to write our null and alternative again. He's looking for evidence of the increase, and we would assume that there's going to be no increase, and we would assume that they would have the same score afterwards. Very important here, their scores would not change. What is the test statistic? Remember, the test statistic is how far away the students scored. The students scored only 3 points higher. This right here is 109. Now 109 is the sample mean. Let's go back to our kind of right here. We're going to have let's delete everything out here and refigure this in, because we are doing a test again now. And we should put this back to n-1. There we go. So putting the notation in is key. His students score a 106, and I put this in the mu naught spot. Very important. So nice and easy. 106 goes in here. Next, we have our sample size. 217 students was the sample. We're so close to figuring everything out. We need the sample mean. From these 217 students, they scored 109. And they had a standard deviation of 8.8. This is the sample standard deviation and the sample mean. Talked about those earlier. And since our sample size is 217, this is a T with 216 degrees of freedom, just n-1. And we will find that out here. So lots of great ways of doing this, because once again, if we have the calculator, nice and easy. Stat, test, t-test. We have the statistics. If you were given data, you could choose that. If you would enter it in under stat, edit, and enter in a list, and then it would choose that list as your data, but we were not given data like that. So let's go to stat test, and let's enter it in. Our hypothesized mean, as you notice right there, is 106. So we hypothesize to be true according to the null. Our sample mean, which is y bar, x bar, just different ways of writing the same thing, is 109. That is a difference of 3. Our sample standard deviation is 8.8, and our sample size was 217. Now, I want everyone to realize here, the math on this is not that hard. And we want to find evidence that the true mean is greater than what we hypothesize, because we want to see that's increasing. When I say the math is not that hard, just realize what you're doing. You're taking the difference right here. We are 3 higher. Just observe the difference right here. And then you are standardizing by s over square root of n. So square root of n, 217, I believe that's almost 15. So you have almost 15 divided by 8.8. And I think this is going to turn to a very large test statistic. Because think about this. 15 squared is 225, I believe. Just trying to remember the math. So 8.8 divided by 15 is something like 0.6. So if you take 3 divided by 0.6, you get 5. And what is 5? It is the standardized difference. And this is not going to really show up on our curve again because it's so far away. So s over square root of n, is the standard error, which is about 0.6 in my book. We'll see if it's however close we are to 5 will tell me however close it is to 0.6. And you can solve this out by hand. Oh, it's very close to 0.6. It must be a tiny bit smaller. It's like, for those who solved it, it's going to be like 0.598 or something. It's very, very close. Because the distance was 3. What am I saying here? Just so you can see, all it is a difference standardized. So if you take 0.3 and divide it by 5.98, oh, I need to put in one more decimal here. 0.598. This is what we're doing in this equation. And this looks to be the right results. And that is basically our T statistic right here. So we've done it in the calculator, and we are so close right here. So what is the test statistic? It is a T, and we need 2 decimal places. I think it was basically 5 point. Let's give it a shot here. 5.02, and we got it. What is the p-value? The p-value is basically 0. Let's see if it likes 0. How do I know this? It's because we landed so far away. If we do a right-tailed test here with the proper degrees of freedom, we should always use. It was 217 for the sample size. That is 216 because every t is different. And we put in our proper t-value of 5.01, and it is basically 0. As in, we landed so far away, this is not likely to happen according to the null. So once again, we would reject the null, and the change is statistically significant. And this means you should buy it. Does the improvement seem to predict significance? Oh yes, and 95% confidence interval, nice and easy. One thing I love about using the TI calculators is if you enter in the data for one thing, it transfers it over, and we've already done a confidence interval. So let's go to T interval here, and let's calculate it. You see it's 95, it's got the sample mean, and it's got the sample standard deviation and the sample size. And we hit calculate, and it will give it to us. If you need to remember how to do a 95% confidence interval, it is on the other questions. And how many decimals? 1. So is it statistically significant? Let's see here. Choose the answer. Does the improvement to be practically significant? Ooh, practically significant. That's a fun one. So let's see what this says. Practically significant means do we actually care about it? And it looks like it's not practically significant because he wants an improvement of 5 points, it seems. So no, a 95% confidence interval only shows a difference between, or excuse me, shows that the true mean would be contained between 107.8. Oops, type it in here. To 110.2. And this does not seem to be practically significant because as students, you know, the true mean after this software is just that they're getting 2 points higher. And I think it said it's a very pricey software. So we probably wouldn't want to do this right here. So it is statistically significant. This is very true because we have evidence that's higher, but the change is not practically significant. So good question on statistical and practical significance, because practical just means look at what's going on here. We're 95% confident the true mean is contained in the interval 107.8 to 110.2, the true mean score of the students. And that's not a real big increase from what they were scoring before at 106. So that does not sound practically significant to me, but statistical significance is just the p-value of the test. And yes, that is statistically significant because the p-value is low enough.